Hi everyone, my name is Vishesh. Um, as you thank, first of all, thank you for coming and attending my talk. Oops. Okay. So I have presented a little bit on another workshop, but I'll present with more props here. We work with soft robots, tensegrity, so there are a few people who love tensegrities, and um, we had a speaker who talked about origami. I always say, joke, tensegrities are 3D origamis. That's how I view it. And then we do sensing and estimation from a soft perspective. Today, my intention of kind of presenting the talk was uh, uh, how can we design robots that can achieve um, reconfiguration? And we're specifically interested in designing robots that can be something like soft transformers that can reconfigure between sphere and a planar configurations. I think the slide is not for here. Everybody loves soft robots. No need to convince. But the idea being, um, it does have applications, like Kwai Jung had pointed out, and we feel the applications also go in locomotion direction is um, soil health monitoring, crop monitoring, aquatic space exploration, etc. Um, we feel that the way robots have transformed, they have gained versatility, adaptability, autonomy. Um, but soft robots, this gap remains. And we feel that the design principles for these kind of reconfigurable soft robots can kind of close the gap very quickly if we design them well. So the question I'm posing is, can we design the soft robot that can reconfigure between spherical soccer-like ball, planar starfish-like, and a unimodal, that means millipede with multiple legs, that kind of. And can they reconfigure between themselves, and can they reconfigure with themselves? So modularity to achieve shape change, or more specifically, dimension change, because the the fun or the impact of that is um, a spherical ball locomotion dynamics is completely different from that of a millipede-like robot or a starfish-like robot. Um, so what we do is we unconventionally look at art. I don't know if many people here have heard about MC Escher. So we went in and just looked at the art, at the tessellations, and got mesmerized. That heavily influenced us, the tessellations of modularities. And we wanted to do modularities on a sphere. We started examining the sports balls, too, like soccer ball. One of the soccer ball, I don't know if you've heard about the Bracusa ball. Has anybody heard about that? One of the Bracusa balls, it's a soccer ball used in one of the World Cups. That became our inspiration. And then we started looking at the concepts of cartography. Um, and here we all know we cannot flatten out a map. And this is where we feel soft robots um, bring their so-called advantages. There's stretchability in there that can compensate for that distortion. And so what we did, we looked at them from um, geometric principles of platonic solids. Oops, where we chose 5 platonic solids and we started to draw along them. And then we projected them onto a sphere, and we started to make these 3-limbed, 4-limbed, 5-limbed robots that could reconfigure to a sphere. And the idea was the number of sides of a platonic solid is number of robots that are required to reconfigure. And as we keep on talking, I'll open a few of them. Um, so for example, this is a 3-limb robot that can reconfigure into a spherical ball. And I'll show you in the next slide too. But like this is a 4-limb soft robot that can reconfigure into, again, these geometrically we only found out the function needs to be odd, but we optimize it for a sine family. Here the important concept was that we are using concepts of geometry, projections, that we typically use in building maps. to do over here. And that was beautiful. Why? Because the designs we came up with, they're scale invariant. What I mean by that is if I build a mold, I can literally stretch it, just like I stretch my scale, my image, like you do in PowerPoint, and the design remains same. The reconfiguration will be into a bigger or smaller sphere, but it will reconfigure the sphere. And then we went on and we tried to do topology optimization. Here we tried to say, okay, we said locomotion ability is proportional to how long the robot arm is, and reconfiguration ability is when they're in flat, how much they overlap, how much is the gap. So I can reconfigure into flat configuration too. And we optimized them and we came up with some topology shapes. So the topology shapes you're seeing over here, it started out with a sine wave and then resulted in such kind of topology shapes. And then we went ahead and we wanted to do motor tendon actuation. And I'll show you a video. I'll show you a video and demo if you want. And then we started designing the so-called morphology of how these robots will be allowed to curl. From that, this is a very couple of years old demo that shows these robots that can reconfigure. At the moment, they're stapled, but they reconfigure. They can roll. Conceptually, things work out from a design perspective, right? And of course, they can do locomotion. They can walk. We have shown them to learn from the environment, do waypoint navigation, and all of that stuff. But why is all of this so cool? It's cool because I can start exploring different topologies now. And you might say that's just an exercise for my brain. No, it's not. So I'll give you an example of why. So what we did, one of the problems that you just saw in that video was they were stapled on. What we did was we were like, no, we want to make them dock. So we embedded some magnets. And turns out magnets, the magnetic force exponentially drops out. So the question was, can we use these geometric principles to design these docking systems? And that's what we are trying to do. We're trying to design these systems with robots on the edge can dock. And it's very tough to pull them out, and yet they remain locked. So that's why these methodologies are very strong. And then the question which we had was, okay, if these can reconfigure into a sphere, these can reconfigure, but what if both of them, one of them gets lost? Can they reconfigure between themselves? So turns out it is. What we did was we fundamentally started with platonic solids, but if you go back a little bit to your high school days or so, you'll remember Archimedean solids. Archimedean solids have polygons of different types. This is a triangle and a square. So this will result in a 4-limb robot, and this will result in a 3-limb robot. So we went ahead and tried to do it, but there was a problem. And the problem was we could forward design, but when we inverse designed it, the vertices would not align. So we went ahead and tried to impose this constraint, vertex alignment constraint, and we were successful. But here the takeaway is twofold. When we have these kind of systems, you have to start defining distortion metrics in both planar and spherical dimensions. Similar to what you have, I don't know if you have gone and become a cartography fan, but you have Tissot distortions and all. So similarly, we need to define for reconfigurability, planar distortions and spherical distortions. And we were able to do that, and as a result, we were able to optimize. So these are some robots in principle we have made design-wise. So I'll kind of quickly conclude that because 10 minutes only, right? So conclude with that thought that we're able to design these robots that can actually reconfigure between all three modes, all three shapes of a sphere, planar, and unimodal, that is millipede-like. And designs are scale invariant, so Do them once, you're done. They can be optimized. You can do run optimization. We've been able to define distortion metrics, so you can start doing what kind of materials you need to select. And morphology wise, you just need to do geometric tuning. With that, thank you. If you have any questions?